All right, so amazing things happened in astronomy as a result of following the European Renaissance. So first we got this Renaissance thing going on around about, the 1400s, earlier than that, starting down in Italy and Florence, where you have these amazing, great works of art being made. You've got Leonardo da Vinci and Michelangelo and Brunelleschi and fantastic stuff, paintings and sculptures and great new buildings being made, totally different than anything that had ever been before. So we've got the Renaissance. And the Renaissance at first is this big artistic movement. Art! Great art, amazing, cool, glorious, wonderful art. How does the art happen? Well, all these people, Michelangelo, Leonardo, Raphael, all these people who are making these stunning paintings, which are just so colossally different than anything anybody had ever painted before. All these things are based on very careful observation of things. They're looking at the world very carefully. They're learning how to use perspective and all these sorts of things. And these sorts of ideas start spreading across Europe. And you know what? If you can do it in art, why not with science? This kind of inspired some people. I think that this artistic movement was very important in saying that, hey, doing new things can be good. We can make sculptures that are better than anything done by the Greeks and the Romans. We can make paintings and buildings which are astonishing. Again, far better than anything that anybody's ever done before. So why can't we do new science? And so people start looking more critically at the works from ancient Greece and Rome. They start looking more critically at the ideas of Aristotle. They start looking critically at the astronomy of people like Claudius Ptolemy. So this inspires to the beginnings of what we now call science and the scientific revolution. The scientific revolution began with astronomy. Astronomy and physics, that was really where it really got going, and then branched off from there to wonderful things like chemistry and biology and finally medicine and all that kind of cool stuff. Anyway, so here's what's going on. So there we go, I can spell. We have Claudius Ptolemy. Ptolemy. He'd written, back in 200 or so AD, somewhere in that neighborhood. Hard to tell for sure. He wrote this great book, the Almagest, named so by the Arabs. The Almagest, the greatest. He has this geocentric model. The purpose of his model is to explain the motion of the planets in the sky. Explain and predict. Key idea for science. Predict where the planets will be. You go to the Almagest, you do your calculations, you say, aha, Venus is going to be located in the constellation Gemini on June 3rd of this year. And then you go and observe there, and hey, it is there, and okay, it works. Except that after 1,000 years or so, the Almagest was off. Its predictions were a smidgen off, and then increasingly off, and Mars was going into retrograde a couple days earlier or later than the Almagest had predicted. So at first, well, what do people do? Well, Ptolemy's almost right, so we'll just tweak this size of this circle and this, and we'll just start things up again, and that works for a couple hundred years, and then it's a little bit off again. Okay, so we got to tweak this, we got to change this, we got to adjust that, and so we've got problems. And so the Almagest is given this geocentric model with the Earth at the center and all the planets moving in circles around the Earth, and then the epicycles on the big circle, epicycles on the deference in order to explain the backward motion. All this is close. It's a good approximation, but it isn't quite right. And so we got some individuals to challenge this model and to say, no, the Earth is not at the center. So the first great person in the Renaissance period who suggested this, his name was Nicholas Copernicus. He was from Poland. So he was Polish, although he traveled around, got educated, all this sort of thing. And this idea, and he wrote a book proposing that the sun is at the center. The sun is at the center. Okay, so he puts the sun, there's our friend Mr. Sun, at the center of the solar system. He has the Earth and all the planets moving in perfect circles around the sun. So we got the Earth moving around in a perfect circle around the sun. And then, so here's the Earth. So his idea is the Earth moves. And then other planets also move in perfect circles around the sun. So you got like Mars going past here. And different planets move at different speeds in their orbits. According to Copernicus, the Earth moves faster in its orbit than Mars does. So Mars is out here and the Earth goes past, and the reason why Mars sometimes moves backwards in the heavens against relative to the stars is because, well, the Earth is moving faster than it. The Earth laps Mars. The Earth leaves Mars behind. It's like, when you're on the freeway and you pass a car and you're both moving forward, but relative to you, that car is moving backward, and so it appears to move backward from your perspective. And so Copernicus wrote a wonderful, amazing book about this. So Copernicus wrote his book, published in 1543. 1543, he writes his book. It's the same year he died. He kind of was worried about this might be controversial, so he noodles around with it for a while, and says, as on his deathbed, he actually saw the first proofs of the book come out. The book is called De Revolutionibus de Orbium Celestium, the revolutions of the heavenly spheres. And in this, he proposes the idea that all the planets move in perfect circles around the sun. All planets move in perfect circles around the sun. This is Nicholas Copernicus's great, amazing, fantastic, glorious idea. Publishes his book, and so there we go. Now there had been at least one ancient Greek who kind of kicked this idea around, but he didn't work out the details, the specifics of the circles. Copernicus did. He said, okay, here's the sizes of all the circles you need, here's the speeds of all the planets you need in order to get this to match the positions of the planets in the sky. And so he does this, and he publishes his book, and the astronomers look at this around Europe, and it's very interesting, and everybody reads his book, and it's all quite fascinating, but it doesn't quite get widely accepted. For a variety of reasons. One reason was, well, they're like, if you're right, Copernicus, then the Earth is screaming along through space at immense speed. Why aren't we left behind? It's like, why don't all the birds in the air, aren't they just left behind by the Earth screaming along at high speed? There were some other issues of, just conservative sort of thinking and all this. What you're saying, Aristotle's wrong? How dare you? He's Aristotle. He's old Greek and dead. You're Polish and alive. Why in the world should we believe you? And of course, then he eventually died. So the death part we can get to, but he wasn't an ancient Greek sort of person. And so there's all these sort of ideas. And here's another really key idea, which people don't always quite emphasize as much when they're discussing it, is that Copernicus's book, if you read his book and you do his mathematics and you do his predicting and you say, okay, where in the sky is Jupiter going to be tonight? And you do his calculations, and they're not exactly dead on. Calculations, predictions were still off. They're not hitting they're not hitting the exact positions of the planets in the sky relative to the stars really much better than Claudius Ptolemy did. Copernicus, Claudius Ptolemy, neither one of them is hitting the nail on the head. So, well, shoot, if you're going to have errors, you might as well go with Claudius Ptolemy. So, this is a big work. It's an amazing work. People trace the scientific revolution to 1543, the publication of De Revolutionibus, the revolution to the heavenly spheres. But Copernicus's ideas were not they didn't immediately take off. So we got to talk about some other people. Here's a wonderfully important person. Tycho Brahe. He was a Danish nobleman. He was, born in the right families, went to the right schools, and he was, very interested in math and astronomy. It's said that once as a student he fought a duel with swords over who was a better mathematician. He lost the duel, and a big chunk of his nose was cut off in that, and so he had this gold nose made. Very eccentric guy. He had this pet moose. Really weird, kind of cool guy. But one of his key, I'd say his big contribution to the development of modern science is he thought in order to solve this problem and to understand and predict the motion of the planets, in order to predict exactly where all the planets are going to be in the sky, his big idea is in order to do that, we need more data. We need more measurements. We need more observations of exactly where the planets are in the heavens. Before that, people had kind of observed, okay, Mars is going retrograde on July 7th, and it's going prograde again on, August 17th, whatever, something like that. No, he said, no, we need to measure precisely and exactly the position of all the planets in the sky every night as accurately as we can for years. And so he, with the support of the king, who he happened to know, it's good to know the king, he created this observatory, Uraniaborg. And in it he observed exact positions of planets relative to the stars every night when it's not cloudy. For years. And now this is all before telescopes. No telescopes at all. Big, giant, amazing brass instruments sighting along till they haven't seen exactly where things are, recording these all in careful ledger books. Lots and lots of data. This is a huge, fantastic, vitally important thing for the development of modern science. Data. Information. The more facts are on the table, the more likely we are to be able to figure out which theory is actually right. That's something you don't see a lot of in ancient Greece. And this was Tycho's great, amazing, fantastic contribution to the birth of modern science. The more facts we have, the more observation, the more specific mathematical measurements, the more numbers we record of the universe, the better we're going to be able to figure it out. So this is his great idea. His thought is he's going to analyze all this data. He's going to figure it out. He's going to solve the mystery of the motion of the planets. He'll be the most wonderful astronomer that ever was, except that before he was able to figure it out, he died. And fortunately, an employee of his was able to solve the mystery. So Tycho Brahe is succeeded by the German astronomer Johannes Kepler. Kepler is absolutely key here. So he works for Tycho Brahe, tries to figure out the motion of the planet Mars, and tries to figure out. Tycho Brahe dies, and he kind of inherits the job and continues working with things. And he's the one who actually solved the mystery of how the planets move through space. Solved the mystery of how the planets move. First of all, he was a huge fan of Nicholas Copernicus. Huge, enormous, giant Copernicus fan. His biggest complaint was that he died too late in life that he could have met Copernicus. That sort of thing. Big Copernicus fan. So anyway, he wants Copernicus to be right. This idea, the planets all moving in perfect circles around the sun, it's got to be right. Only Copernicus probably just got the wrong size of circles. And Kepler thinks if I can just tweak the size of the Earth's circle and the Mars circle and all this, I can get it to work. And so he works on this for years and years, analyzing the data, measuring the numbers. He works and fails. And he can get it close, he can get it achingly close, but old Tycho had estimated the error of his observations, and Kepler couldn't get it within the error of those observations. He could get it close, couldn't quite get it there, and he didn't want to fool himself, and he didn't want to deceive himself, and he said, okay, I'm wrong. Copernicus is wrong. Maybe the planets do not move around the sun in perfect circles. Maybe they move around the sun in other shapes. And he starts trying other shapes, and he figures it out. The planets move around the sun, not in perfect circles, but in ellipses. An ellipse is a geometrical shape. It's kind of like a squashed circle. It's like a circle where, the circle is a set of all points. I can't even draw it well. The circle is a set of all points where there's an equal distance from the center. With an ellipse, an ellipse is going to be similar to that, except that with an ellipse, what do you got? With an ellipse, you got two focus points, and if you add up the sum total of the distances to all the focus points, this distance and this distance, you add them up, and you will get the total that remains constant as you go around the ellipse. And when Kepler tried this out, it worked. So that's Kepler's first law. Planets move around the sun in ellipses. Second law describes how they move faster when they're near the sun. So here's the sun. The sun appears at one of these two focus points. The other one's just empty space. And when they're near the sun, they move faster so that they sweep out an equal area here as they do in the same period of time when they're out here. You see, this triangle is longer, but it's moving slower here. So this is shorter, this is longer, and that tells us exactly how much faster every planet moves when it's closer to the sun. And then even more amazingly, he figured out that if you take the period of time it takes for every planet to orbit the sun, and you square it, and you measure the period of time in years it takes to orbit around the sun, and you measure the distance from the sun, and you cube it, you measure the distance from the sun in AU. The Earth is 1 AU from the sun, and this is in years. you find that these two things are equal to each other. The period of time to make an orbit in years squared is equal to the distance from the sun in AU cubed. A crazy, weird, fascinating mathematical pattern. That Mercury takes less time to orbit the sun than Venus. Venus takes less time to orbit the sun than the Earth, and it goes out from there. And he figured out an exact, detailed, precise mathematical pattern. The planets move in orbits around the sun in ellipses. They move faster when they're near the sun, and p squared is equal to d cubed, and that's amazing.